Hi, everybody. I hope everyone is ready for another fantastic round of chemistry, and more specifically, our last lecture on stoichiometry. Believe it or not, this is our 11th lecture now, and looking through our schedule, we will probably have 22 lectures on the semester, and so once you are done watching this lecture, you're actually halfway through the lectures and the material for this course. And so we are getting there. We're getting through quite a bit of material, and so stay buckled in, keep working hard, and we will get there. And so last time we started looking at some of the different types of analysis that we can do with stoichiometry and some of the ways that we can really use some of these principles in some real chemical analyses. And so there's only one warm-up question today, but it is going to take you a little while. It's involving a combustion analysis, which those are calculations that you, as you know, are fairly intense, and so they might take you a bit to get through it. And so here it is. And so we have a certain sample of menthol. When combusted, it produces some carbon dioxide and water for us. And so from this, we want to be able, we want to calculate menthol's empirical formula. Excuse me. Menthol does contain only carbon, hydrogen, and oxygen atoms. And so from this, you should be able to use what we talked about last time and find the find the empirical formula for menthol. So go ahead and pause the video now. Work through this calculation. It should take you a little while to do. And then when you're done, fire the video back up and we'll compare answers. And so this shows you actually all of my work that I did for this one. Came up with a final empirical formula of C10H20O. And so let's just take a quick look at what I did for this. So our general formula for this hydrocarbon, we know it contains only carbon, hydrogen, and oxygen. And so I just wrote out a general formula of CXHYOZ. And so to find our empirical formula, we want to find X, Y, and Z. And so for our first step our first step is to try to convert all of our given amounts to moles. And so I take the amount of carbon dioxide that we had, I convert that over to moles of carbon dioxide. I have 1 mole of carbon for every mole of CO2, and so I get 0.006428 moles of carbon. I can do the same for hydrogen. Well, to back up, and remember that had to have been the amount of carbon that was present in my initial sample. So that had to be the amount of carbon present in this 0.1005 grams. We do the same for hydrogen. We use our amount of water, our grams of water, convert that to moles of water. We do have to remember that there are 2 moles of hydrogen in every 1 mole of H2O. And so that tells us that in our initial sample, there had to have been 0.01287 moles of hydrogen. To get to the moles of oxygen, remember, it is a little bit more complicated. What we're going to do there is take the amount of moles of carbon that we had and the amount of the moles of hydrogen, convert those over to grams. That's what I'm doing here in these first 2 steps. So we have our amount of grams of carbon and our number of grams of hydrogen based on our number of moles of each. And then we're just going to subtract those from our total amount that we had. Because we know this substance only consists of carbon, hydrogen, and oxygen. And so if I know how many grams of carbon there were and how many grams of hydrogen there were, the rest must be grams of oxygen. And so we find 0.01032 grams of oxygen. And then finally, we convert that over to moles. And so then our last step in finding empirical formulas is to take all of the molar amounts and divide them all by the smallest number. So the smallest number for these is let me back up. That was the amount of grams leading us to, for oxygen, giving us a molar amount here of 0.0006452. And so that's our smallest molar amount of the 3 of these. And so we'll divide all of them by this. So we divide our moles of carbon by that number, and we get pretty much 10, it's 9.96. We do the same for hydrogen, our 0.01287 divided by 0.0006452, and we get basically 20, that was 19.94. Then this number divided by itself for oxygen is 1. And so that 10 was our subscript for carbon, C10. The 20 was our subscript for hydrogen, H20, and the 1 our subscript for O. And so our empirical formula then for menthol is C10 H20O. And so what I want to do now is I want to show you why this sort of analysis is important and what we can really do with this, or where this might fit in to some real type analysis. Because this isn't something that chemistry teachers and chem professors just make up to have you do for busy work because we don't like you. This is a real sort of analysis that might be done. For instance, if somebody has a completely unknown substance of some sort and they want to try to find out what it is, excuse me, they're not going to be able to find out what it is simply by finding the empirical formula. But that's one step in the overall process. And so let's take a look at some things that might be done here. And so if we're starting out, let's say somebody comes to us with this completely unknown compound. They have no idea what this is. It's just this white powder. They want to know what it is. Well, this is one of the first things that might be done is that combustion analysis, which gives us our empirical formula. And so we've got this unknown compound. Somebody brought it to us. We're working in the CIS lab. Somebody brings this compound to us, and so we run it through our combustion analyzer, and we do these calculations that we've been learning, and we find that the empirical formula of this compound is C10H20O. We also find, we put this into a mass spectrum, and it shows the compound here. It wouldn't show that, obviously, if this was an unknown compound. But we put this into an instrument called the mass spectrometer, our unknown, and it gives us what we call a mass spectrum of the sample. We do that, and the data reveals an actual molar mass of 156 AMUs. Now, remember what we looked at with converting our empirical formulas to molecular formulas. And so what this does for us is this tells us that not only is the empirical formula CH20O, it also tells us that the actual molecular formula for this unknown is also C10H20O. Oh, and I've got to make sure to adjust my slide here. So it means the molecular formula is also C10H20O. I'm actually going to fix that right now while I'm thinking of it. And we're back, all fixed. So what we've done here with our unknown, we sent it through our combustion analysis. We found an empirical formula of C10H20O. We put our unknown into a mass spectrometer, and doing that got the molar mass for us, so that we now know that the actual molecular formula is also C10H20O. We would then look at some other types of analysis in order to figure out what this compound is. We would take a look at what we call an infrared spectrum. We would use an infrared spectrometer for this. And we would get something that looks sort of like this in the case of our particular unknown here. And I definitely don't, I mean, you guys have no idea what you're looking at here. Don't worry about that. I'm sort of showing you some of the things that we would do, some of the ways that we would figure out what this unknown is. Those of you eventually going on to organic chemistry, you will be analyzing spectra just like this. You will be running your own infrared spectrum analyses and using that to help identify some compounds. So this would give us some information about the compound. We would then also run what we call NMR, nuclear magnetic resonance. We would do both a hydrogen NMR and a carbon NMR. This is what our hydrogen NMR would look like, and this is what our carbon NMR would look like. And again, those of you going on to organic, you will be doing your own NMR analyses as well. But then we would use all these pieces of the puzzle. We would use what we know for our empirical and then our molecular formulas. We would look at our infrared spectra. We would look at both of our NMR spectra. And using all of that is when we would eventually be able to come up with a full, complete structure for this unknown compound. And we can see here, so our C10H20O, and this is just the way we write things for organic molecules. We simplify it a little bit. But we can see our C10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 hydrogens, and 1 oxygen. And so the empirical formula, the combustion analysis that got us to the empirical formula was a key part in being able to identify the full-on structure of this unknown compound. So again, I wanted to go through that to really show you that this isn't just busy work. This is a real sort of analysis and a real sorts of calculations that might have to be done to try to identify something that we don't know what it is. And so this is a real analytical tool that might be used by scientists for various reasons. And so with that being said, that is our only warm-up question for today. And so let's go ahead and get into our last bit of stoichiometry. And so for our last stoichiometry lecture, we're going to really focus in on solutions. We've talked about how solutions play into stoichiometry a little bit, and we've looked at molarity a little bit. But today we're really going to focus in, and we're also going to talk a little bit about pH and how pH is used as a measure of the acidity, and it's really reflective of the concentration of particular types of ions. And then we're going to look more in depth at the stoichiometry that's involved in solutions. And so most experiments in general, or most chemistry, is going to take place in aqueous solutions. Or a lot of chemistry anyway, is going to take place in aqueous solutions. And so we need ways, or we need a way to measure the solution concentration. We need a way to measure how much of our compound of interest is actually dissolved into the solution. And so we use a unit called molarity. This is something, those of you that are in 114, this is something that you've talked about in there. We've used molarity in module 2 a fair bit. And what molarity does is it gives us the amount of moles, the number of moles of a substance dissolved in 1 liter of our solution. And we'll look more at those units in a little bit. But it gives us a measurement and a way to know the amount of that compound that's in a sample of the solution. Solutions in general consist of a solute and a solvent. The solute is the thing which is dissolved into the solution, and it's always the thing that's in a lesser amount. The solvent is the thing that is doing the dissolving, so to speak, and it's going to be the thing that's present in the greater amount. Very typically, for the vast majority of things that we do, water is going to be your solvent. And so in this case, for instance, we're taking some copper sulfate. Here's some clear copper sulfate here. And that was dissolved into the water to make this copper sulfate solution. And so the copper sulfate was our solute, and the water was our solvent. I use the terms lesser amount and greater amount here, though, so that you don't necessarily think that water is always going to be the solvent. If you, for instance, have a sample of 95% ethanol, that 95% ethanol is made, 95% of that is actually ethanol. The other 5% is water. And so in that case, you have a solution, but water would actually technically be your solute, and the ethanol would be your solvent. And so just be aware of that yes, most of what we do, water is going to be our solvent, but that's just because we use water to dissolve our substances in. And so molarity, as we mentioned briefly a little bit in lecture, and as you've started to look at more in depth in lab, molarity is a measure of the moles of solute per liter of solution. Now note here that that's not per liter of solvent. So that's not, for instance, per liter of water. That's per liter of the entire solution. And so that includes the amount of solute that's in there. It's a really simple calculation, though. You just take your moles of solute and divide that by how many liters of solution you have. This is the way that we would express it. And so, for instance, the concentration of NaCl, these brackets here simply mean concentration, typically in molarity. So anytime you see something in chemistry, if you see it in those brackets like that, that just means that we're talking about the concentration of, in this case, NaCl. And so here we're talking about a 1 mole per liter solution, and we express that as 1.00 molar. Big M stands for molar. And so this would be a 1 molar solution. Now take note here that when we're looking at these units, and so in this case, it's 1, but it could be anything. Let's say, for instance, in lecture, we were dealing with 0.025 molar solutions. So that's 0.025 molar. If we actually write the units of that out, say, for instance, our ammonium nitrate solution we worked with in lab, that's moles of ammonium nitrate per liter of solution. What does this now look like? Hopefully you said it. This is a conversion factor. It's just another conversion factor. It's the way that we're going to transform back and forth between moles and liters. And so the way that we set this up would be completely dependent on what we were trying to calculate. If we knew the number of liters and we wanted to calculate the number of moles, so if we knew, for instance, that we had maybe something like 4 liters, then okay, we're going to set this up like this, and we're going to get an answer of 0.10 moles of the ammonium nitrate. If we were going the other way, if we knew the number of moles and we wanted to calculate the number of liters, so if we knew that we had maybe 2.0 moles, then okay, we're just going to go the other direction. 2.0 moles, 1 liter, 0.025 moles. I actually haven't done this out yet because I'm just sort of making these ones up as I go, but 2 divided by 0.025 means that we would have 80 liters of solution. So it's just a conversion factor. We use it like we would use any other conversion factor, moles per liter. And so it's just going to completely depend on what we're trying to calculate as far as how we are going to use this conversion factor. And I should have known or remembered that I had the other big slide right there. And so molarity, moles per liter. Now definitely note that the volume does have to be in liters. So you may have to convert depending on what you're given. It's actually fairly uncommon for us in the lab to work with liters of solution. That's just a lot. A liter is a lot of liquid. And so it's much more common for us to work in terms of milliliters. And so you may have to do those conversions. You may have 50 milliliters of your solution. And so you would have to convert that to liters before you can use a calculation involving molarity. I've shown this before. And so again, this is how molarity sort of fits into this whole pattern, this whole pathway of converting to moles. And so moles is still central. We're working with stoichiometry here, where moles are central to every single calculation that we do. Molarity now just gives us another tool, another way to be able to get there. And so we can use molarity, or to get back and forth for a number of moles. And so a solute, as I mentioned, is typically a solid, and quite often or will typically be some sort of soluble salt, some sort of ionic compound, or something that's a soluble covalent compound, something like sugar. Sugar dissolves in water pretty readily. That's a covalent compound, so that could be a solute. The solvent, as I mentioned, is considered to be the major component, normally going to be water. Now, one of the more common things that might be done in a lab is having to prepare our solutions, having to actually make, for instance, in this case, somebody wanted to make, it looks like that's a 100 milliliter flask. So somebody needed to make 100 milliliters of the 0.1 molar solution here. And so we need to figure out how to do that. We need to figure out how to actually make a certain amount of a certain molarity solution. And so keeping in mind, and I know that I talked about this in my labs when we talked about module 2, but what that means is that most of our chemicals, most of what we have in a storage room, for instance, most of those chemicals exist in a solid form. It's just the convenient way for us to be able to store them. And so if we want to then make a solution out of that chemical, what we need to do is, well, we need to know how much of the solution we're trying to make and what the molarity of that solution needs to be. And once we know that, what we have to actually physically know in order to make the solution, so keeping in mind that it's a solid, and usually a lot of ionic solids look kind of similar to salt or sugar, sort of just this crystalline or powder sort of form. And so what I need to know is how much of that solid do I need to weigh out? How much of that solid do I actually need in order to make the solution that I'm looking for? Once we know that, then we add it into typically quite often a volumetric flask. They look like this, and you can't probably see it on your screen, but there's a little line on this one right here. And this is a 500 milliliter volumetric flask. The sole purpose of this piece of glassware is simply to make 500 milliliters of a solution. And so the way that I would make this solution is I would actually probably put a little bit of water in here first. Some people do that, some people don't. Doesn't really matter. But then whatever amount of solid that I calculated I needed, I would weigh out that amount, and then I put that into my flask, and then I add enough water until I get up to this line, again, which you can't see, but there's a little line right here. That line marks 500 milliliters. And so again, when I'm making a solution of a known molarity, that liters of solution, that volume, is the volume of the entire solution. That's why I need to add in the solid first, or I need to add it in before I get to my full volume at least. And so once I get to that full volume contains both the solute and the solvent. And so I would not simply add my solvent or add my solute and then add 500 milliliters of water, because that might be too much, because that hasn't taken into account the volume that the solid is going to take up. So I add in my solid and then enough water to get up to my desired volume. And then I just invert the flask a few times, and I can give you a little example here. I'll do something like this. You know, I'm inverting it in order to mix it up. And so just sort of showing, again, sort of what that process would look like. So in this case, we're looking to make, actually I don't see what the molarity is, but we're looking to make a solution of potassium permanganate. So this nice purpley color. And so in order to make whatever concentration solution that we're trying to make here, we needed to measure out 0.435 grams of our solute. We add that 0.435 grams into our volumetric flask. And then quite often we add just a little bit of water, enough to just dissolve the substance completely. And so then once it is fully dissolved, then we add enough water up to the mark. And we'll quite often use this little squirt bottle like this, because that allows us to be more precise and add water very slowly until we get right to our mark. And so let's look at an example here. And so if we dissolve 0.395 grams of potassium permanganate in enough water to give a final volume of 250 milliliters of solution, we want to know what the molarity of that solution is going to be. So go ahead, if you think you can do this, and you have the tools. I've taught you all the tools now to be able to do this. Go ahead and pause the video and see what you can come up with, and then we'll look at the solution. So let's take a peek. So the answer is 0.0100 molar. The key thing to remember here is that the concentration units, the units of molarity, are moles per liter. And so what I want to do first is take my grams, take my mass of my solute, and I'm just going to use the molar mass to convert to moles. So I see that I have 0.0025 moles of solute. And so then I'm going to divide that by the liters of solution. Now here's where, like I had mentioned, we have to do a little converting, because we were given 250.0 milliliters, but we have to be in units of liters for our molarity calculation. So we're just going to convert 250 milliliters to liters. Remember, your conversion there is 1,000, so we're going to divide this by 1,000 to get to 0.250 liters. And so then 0.0025 divided by 0.250 gives us 0.0100 molar. Let's just look at the Sig Figs real quick. And so, because I think some of you might be looking at this saying, oh, well, that's 2 significant digits here, Professor Staples, but you have 3. This was sort of an intermediate step. And so keep that in mind when you're looking at your Sig Figs. For our Sig Figs, we're always going to be looking back at our initial amounts that we were given. Our initial measurements, the fewest number of Sig Figs was 3. And so our answer here then has 3 Sig Figs. And so make sure that you're going by what we're initially given for information. And so in this example, and I actually just blew it and showed you the whole thing here, but here we're dissolving 5 grams of our nickel 2 chloride and then hexahydrate. We haven't really looked at hydrates, but hydrates are just compounds that have water attached to them as well. And so we have to take these 6H2O into account in the molecular weight of the compound. But we're dissolving this 5 grams of nickel 2 chloride hexahydrate in enough water to make 250 milliliters of solution. And so it's the same exact process. We're going to take our 5 grams, convert that to moles, divide our number of moles by our number of liters, and we're just doing the conversion right here. And that gets us to 0.0841 molar solution. Now, let's just take a look at what this means for different ion concentrations. One of the things we have to keep in mind is that the number of ions in any solution is going to depend on how that compound dissociates in water. And so, for instance, copper 2 chloride, when it dissociates, we're going to have our copper 2 plus ion, but we also have 2 chloride ions that we can see here. And so for every 1 copper 2 chloride, for every one of these, I'm going to get 1 copper ion, but I'm also going to get 2 chloride ions. So what that means for the molarity, so if I have a 0.30 molar copper chloride solution, copper 2 chloride, that means that when it dissolves, my concentration of copper is going to be the same, because for every one of these, I produce 1 copper ion. But for every 1 copper 2 chloride, I get 2 chloride ions. So my concentration of chloride ions is actually going to be 2 times my molarity at 0.60. So we have to keep that in mind as well. And so try some of these questions here. And so go ahead and just pause the video and see what you can come up with for answers to these, and then we'll come back and see what you got. Hopefully you were able to come up with these answers. If not, again, go back and maybe check what you did wrong, or check in with me, shoot me an email, bring it up during an LA session perhaps, or if you're going to the tutors, which I highly recommend, see if they could help you out if you got some of these wrong. Let's look at what we would need to do in order to figure out how to actually make a solution by dilution. Actually, let's back up, because there's one type of calculation that I haven't shown you yet. And so let's say, for instance, that we wanted to make, let's back up. Let's say we wanted to make this solution right here. So we want to make, I'll say, 350 milliliters maybe of the 0.250 lithium carbonate solution. And so we want to make this solution. And so again, I know that this was a calculation that I did go over in my labs for 114, and hopefully your instructors did too, but let's take a look at it here as well. And so if I want to go into the lab and make this solution, and I'll put a little decimal point here, so I want to make exactly 350 milliliters. So what I need to know is how much of the lithium carbonate, how much of that solid lithium carbonate do I actually need in order to make this solution? And so the first place that I would start here is I would start with the volume that you're given. And I'm going to go ahead and just convert that over to liters automatically. So 350 milliliters is 0.350 liters. For my next step, so again, keeping in mind that our goal is to figure out how many grams of the solid that we need. How many grams of the solid lithium carbonate do I need? And so for my next step, I'm going to use the molarity. So I'm going to convert from I'm going to use my liters and my molarity to convert to moles of the lithium carbonate. And so 0.250 moles of my lithium carbonate per liter, because that's the very definition of molarity. And then my next step is just to use my molar mass of lithium carbonate. And so I find that to be 73.891 grams of lithium carbonate per mole. And we look at our units, we see that liters have canceled out, moles have canceled out, and I'd be left with grams, which is what I'm looking for. And so then we pull out our trusty calculator, 0.35 times 0.25 times 73.891. And I get a mass of 6.47 grams. And so this tells me, again, keep in mind what this actually gives me for information, is if I want to make this solution, if I want to make 350 milliliters of a 0.250 molar solution of lithium carbonate, I need to get the solid lithium carbonate from the back room, get it off the shelf, get my little bottle of solid lithium carbonate. I then need to weigh out 6.47 grams of that solid. I'm then going to add that into my volumetric flask and then add enough water until I get to a total volume of 350 milliliters. When I do that, I will have 350 milliliters of my 0.250 molar lithium carbonate solution. This is an incredibly, incredibly common calculation to do in a chemistry lab. Solution prep is one of the most common things that just has to be done to get ready for any sort of work. When I was a high school chemistry teacher and I had to prepare all the stuff on my own for labs, I would have little Post-its full of these calculations all over the lab. Anytime that I had to get things ready, I'd have to run this calculation. So I'd pull out a Post-it, throw this calculation together, and believe it or not, it would look pretty much exactly what this looks like here. I don't just set things up like this just as a way to show you and to teach you. This is really how I still set things up when I run calculations. And so there would be Post-its like this all over the place quite often. This is a real type of calculation that is done constantly in various types of chemistry labs. So sometimes though, so quite often, yes, we have in the stock room or in storerooms, we store our compounds in their solid form, but sometimes we do get things that are stored in a liquid form. And so, or we have a solution that's already made, but we want a solution that's not quite as concentrated. And so in those cases, we have something that's already in aqueous form. We have an already aqueous solution, but we want to make some of that solution at a lower concentration. And so what we need to do there, so like in this example here, so in this example here, we have 0.100 molar potassium dichromate. Dichromate is one of the polyatomic ions that I didn't make you memorize. It's not as common of one. But a 0.100 molar potassium dichromate solution. And what we're trying to do here is make 500 milliliters of a 0.00100 molar. And so we want a solution that's 100 times less concentrated. And so what we need to do is figure out, so again, sort of thinking about exactly what we need here, what we want. It's the same idea what we need to do is figure out how much of our original solution that we need to then add that to our flask. And here they figured that we needed 5 milliliters of the original solution. We take that 5 milliliters of the original solution, in this case using a volumetric pipette. And so that 5 milliliters of original solution, transfer that into our 500 milliliter volumetric flask. This would be the same thing as transferring that 6.47 grams in, same exact idea. And then we add enough water to get to our total volume of 500 milliliters. And once we do that, now we have 500 milliliters of the 0.00100 molar solution. So it's the same exact idea. And what we need a way to do is we need a way to figure out how much of the original solution we need. So for any time that we're doing something like this, we use what we call the dilution equation. M1V1 equals M2V2. And in these cases, typically the amount of solvent is going to increase because we are diluting it, but the amount of solute stays the same. And that's the key. And that's why this equation works. The amount of solute stays the same. So your number of moles of the solute remains constant. What changes is your volume. And so that means that your molarity changes. And so M1V1 equals M2V2 just works out to the initial moles that we had is going to be equal to the final number of moles that we had. And so the M1 refers to the initial concentration of your initial solution. And so M1V1 equals M2V2. M1 equals your initial concentration of your initial solution. V1 equals the initial volume of that first solution. M2 is the new concentration of your new solution. And V2 is the new volume. And like any sort of a formula like this, as long as you know 3 of these variables, you can find the other one. And that's the way that we would typically use this. And so, for instance, in this question here, so we need to know what volume of 12 molar HCl is required to prepare 100 milliliters of a 1 molar solution. So again, this is very, very, very similar to what we were just looking at with the calculation where we needed to find mass. In that calculation, we needed to know the number of grams that we needed to dissolve into a solution. Here, we're starting with an aqueous solution already, so we just need to know how much of that 12 molar HCl do we actually need. And so we're just going to go ahead and use our M1V1. Sorry, let me just adjust that. There we go. M1V1 equals M2V2. M1, our initial solution, is 12 molar. That actually is rip your face off concentrated acid. That's 12 molar hydrochloric is very nasty stuff. V1 is what we're looking for. How much of that rip your face off acid do we need? M2 is our target molarity, so 1.0 molar. V2 is our target volume. What's nice about this equation is that even though, yes, molarity is in terms of liters, we can leave our units in milliliters here. We're just under the understanding that once we calculate V1, it will also be in milliliters, but we can leave that right alone. So we're going to get 1.0 times 100.0, all divided by 12. And so we get a V1 of 8.33 milliliters. And so this means that in order to make the solution, I'm going to take 8.33 milliliters of 12 molar HCl. I'm going to add that into a 100 milliliter volumetric flask. I'm then going to add enough water until I get up to my total volume of 100 milliliters. And that's how I would have made the solution. So go ahead and try this next one on your own and find the concentration of a solution that's made by preparing, or it's made by diluting 25 milliliters of 14.8 molar nitric acid to a final volume of 1.5 liters. So we're taking 25 milliliters of this concentration. Here's Rangeley coming in to say hi to everybody. Say hi, Rangeley. We'll let him say hi real quick, and then you can do the calculation. There he is. Hi, kitty. Say hi. All right. Let me finish this lecture, and then we'll play. Okay. And so, oh, okay, what's going on? Here we go. So go ahead and try this one then. Trying to find the new concentration of after we've diluted this nitric acid. So go ahead and pause the video and see what you can come up with. Hopefully you came up with the solution is going to be 0.25 molar. Let's switch gears a little bit and talk about pH and pOH. Now, acids and bases are typically over a very, very wide concentration range. When we look at, as we mentioned with acids and bases before, what we're really concerned about, especially we'll focus on acids, that H plus is really the component that makes something an acid. That H plus concentration in a solution could be anywhere from like 10 to the negative 13th molar all the way up to maybe a 1 molar H plus. And so a huge, huge, huge range could be possible when we're talking acids and bases. And so we need a convenient way to express those. That convenient way is the pH scale and pOH, for those of you that haven't heard about that. pH and pOH give us a convenient way to keep track of those incredibly large ranges. We do that by using a log scale. Sorry, let me blow this up a little bit for us. Here we go. So we do that by using a log scale, which allows for factors of 10. When we calculate pH, we take the negative log of the H3O plus, remembering that H3O plus is analogous to H plus, same thing. So we're going to take the negative log of that H3O plus solution concentration, remembering that brackets just mean concentration in molarity. Likewise, pOH is the negative log of the OH minus concentration if you happen to be given that instead. There is a relationship here, and it's a relationship that you'll explore in more detail when you get to CHY 115, for those of you going on there. pH plus pOH equals 14. And that is an important relationship for us to remember as well. And so the way that you would put this into your calculator would depend on, if you're calculating pH, and that is going to depend on what type of calculator you have. Geez, here it is, lost it. So let's say that we have, for instance, a 0.025 molar concentration of H plus. And so in this type of calculator, all we do then is we're just going to hit the log 10 right here. And then we need to take the negative of that. And so the pH of that solution would be 1.6. If you have the TI type of calculator, something like this, if I can do this backwards, I can't. What you would do is you would just hit your negative. So you're going to hit your negative key right there. Negative. Oh, maybe I can do it. Oh, I'm backwards. Negative log. There it is. So you're going to do negative log of what I say this one was, 0.025. So if you can see that, negative log of 0.025, and then I can press enter. Oh, I missed it. And I get my 1.6. So again, it's just going to depend on the calculator type that you have. But that's how you would calculate the pH. And so go ahead and try some of these. Try using those relationships. See if you can find the pH of an acid that has a pOH of 11. Find the pOH of a base with a pH of 8. And the pH of an acid with a pOH of 11. So again, just using what we looked at with these relationships here. Oh, and hopefully you came up with these answers. So here we're just sort of looking even closer at that power of 10 relationship. And so like I mentioned, we're looking at very wide ranges. So we could have hydrogen ion concentrations of anywhere from 1 times 10 to the first, all the way up to maybe like 1 times 10 to the negative 12th, or down to that. And so that would give us these resulting pHs. Oh. And so calculate this. I just showed you the answer. But go ahead and just calculate the pH of this solution. And so the hydrogen ion concentration, our H plus concentration, is 1 times 10 to the negative 9th. So do negative log of 1 times 10 to the negative 9. And hopefully you get a pH of 9. Sometimes you need to go the other way. Sometimes you're given the pH and you want to find the actual hydrogen ion concentration. And so if you're not familiar with the mathematics of logs, that's fine. I'll just tell you that what you do is you raise 10 to the negative pH. And so 10 raised to the negative pH will give you the hydrogen ion concentration. So in this case, it's going to be 10 raised to the negative 7th power. Now, most of you are probably somewhat familiar with the pH scale. You've talked about it in other science classes. You know that the neutral is considered 7. Anything below 7 is acidic. Anything above 7 is basic. And so this just gives you an idea here of a few different types of solutions. So vinegar, for instance, pH of about 2.8, pretty close to most sodas, which is about 2.9. Oranges and citrus are pretty acidic at about 3.8. Blood is actually slightly basic at about 7.4. Then a lot of some various household cleaners are actually fairly basic. Ammonia, for instance, at 11.4. Oven cleaner up at 11.7. And so just sort of give you an idea of where some things sit on the scale. So lastly today, we're going to talk some about solution stoichiometry. And we've actually talked about some of this before. So I'm just going to go and skip the slide and go right to here. So when we first started talking about stoichiometry, we looked at this relationship here, or this sort of flow chart, where we're quite often given the mass of one substance, and we're going to then convert that to moles of that substance, and then use our equation to convert to moles of the substance we're looking for, and then use the molar mass of that substance to find the mass of it. So we've looked at that flow, and you've hopefully done a ton of problems that look similar to this, or using this flow. And remembering that at the heart of this is that molar relationship, and we use the stoichiometric ratio from our balanced chemical equation. And in order to get to the moles, we use our molar mass. This solution stoichiometry, we've already talked about it. You've already maybe done some calculations like this with some of your practice problems. But this solution stoichiometry, all it really does for us is it gives us another avenue to get to moles. It just, now if we have the volume of an aqueous solution, we simply use the molarity to get to number of moles. And so it just fits into this pathway. And so just like we've seen here, sort of our very beginning slide, looking at this whole pathway with stoichiometry. So it just means that we would be sitting right here. This would be our aqueous solution pathway here. If we have an aqueous solution, we would be given the volume of that, and we would use the molarity to convert to moles of that. And then to then be able to go anywhere. Like I said, you've already looked at some examples of this. I know that a couple examples that we saw that I think were in previous lectures were, for instance, you have two different aqueous solutions. You mix those together and you form a precipitate. And we want to know what the mass is of that precipitate. Then you would just say, boom, okay, well, I'm starting right here with an aqueous solution. So I'm going to convert to moles of that aqueous solution. Maybe it's even a limiting reactant problem. So it's a little bit more complicated, but it's the same basic idea that you determine your limiting reactant, and then you use the molarity to convert to moles of whatever the limiting reactant is. Use your stoichiometric ratio to convert to moles of what you're looking for. In this case, would be moles of the precipitate. And then you can use the molar mass of that precipitate to convert to grams of it. And so that's what solution stoichiometry does for us. is it just provides us with the tools that we need to look at some of the other pathways in stoichiometry problems. Oh, okay, and so this question here, same idea. Actually, it's actually the exact example that I was just talking about. We want to know how many grams of calcium carbonate can be consumed. It's actually sort of, yeah, so no, it's the exact same thing pretty much. But how many grams of calcium carbonate can be consumed by 35 milliliters of 0.125 molar H2SO4? It's only the only difference here is that we're looking at two of the reactants. So we're given an amount of H2SO4. We want to know how much calcium carbonate can be used up, can be consumed by this amount of H2SO4. And so it's the exact pathway that we just talked about. We're going to take our milliliters, our volume of H2SO4, use our molarity to convert that to moles of H2SO4, use our balanced chemical equation to then convert, oh, sorry, there's, oh no, sorry, it's correct. I thought there was a mistake in my equation, but there isn't. So take your moles of H2SO4 and then convert to moles of your calcium carbonate, and then finally your molar mass to convert to grams of calcium carbonate. So go ahead and pause the video and give this a run. Pause the video and try this and see what you can come up with. Hopefully what you came up with was 0.44 grams of calcium carbonate. If you didn't, then look through my steps here and see where your steps might have been different from mine. We also sometimes have to do what we call standardizing a solution, or using, yeah, we have to standardize solutions, sorry. Because sometimes we can't make, I'm trying to think of how to say this. If we're trying to make a solution, we can't always trust the mass accurately. So some solutions just simply can't be accurately made by the weight and dilution methods. Sometimes maybe the solute is impure or maybe unstable, so we don't know that the mass is a true reflection of the actual compound of interest. So in that case, what we can do, and this is something that we'll be doing in the lab in Module 4, what we can do is we can make a solution that's close, that we know is close to our target concentration, and then we can standardize that solution against something that is stable. And we quite often will use a technique called the titration for that, where in a titration, we have two aqueous solutions, and we're going to talk about acid-base titrations here. And so when we titrate, and you'll see this procedure in lab, but what we do is we use an indicator which tells us when a reaction is done, at which point the moles of our standard, so the moles of our stable compound here, are going to be equal to the moles of the solute reacted. And so actually, let's just look at an example. And so this would be an example of a titration. In this case, we have a burette. That's what this instrument is called here. This is a burette, which contains a base of a very precisely known concentration. So we know the concentration of the base that's in this burette. We have some sort of acid down here that has a concentration that we don't know what it is. And so we're going to perform the titration. We're going to add base from the burette here down into our flask. And we use this indicator, in this case, an indicator called phenolphthalein, which turns pink when our reaction is done. At that time, at the instant that our indicator turns the reaction pink, we've added exactly enough moles of the base to be equal to the moles of acid that were down here in our flask to begin with. Using that, we can calculate the molarity because we know what the volume was here in our flask. And so this is just sort of going through what the various steps are. I won't spend much time there. But this shows you exactly how you would do the calculation here, or in a lot of instances. And it's just a different pathway. But it's the same idea. We're still going through moles of the compound. And I know I kind of blew through that, but let's look at this example. So this would be a very typical sort of example that you might look at. And so we want to know what volume of 0.600 molar hydrochloric acid is required to neutralize 25 milliliters of 0.175 molar hydrochloric acid, or sorry, 1.175 molar NaOH. And so let's just take a look at what that calculation would look like. And so in this case, so we're given, we want to know the volume of HCl. So we need to look at our balanced chemical equation. HCl plus NaOH is going to give us NaCl plus H2O. Remember our general acid-base equations. So we know it's a one-to-one relationship. We're told that we start with 25 milliliters of our NaOH. And actually, I'm just going to make things easier so I don't run out of space and just convert that over to liters right from the start. .025 liters. And so that's liters of NaOH. Then I'm going to use my molarity, 0.175 moles of NaOH per liter. I have a one-to-one relationship here. And so 1 mole of NaOH to 1 mole of HCl. And then finally, I know that it's a 0.600 molar solution of HCl. I need moles of HCl to cancel. So now my 0.600 moles of HCl goes down bottom, and 1 liter of my HCl solution up top. I plug this into my calculator. 0.025 times 0.175 divided by 0.6. I find that I need 0.00729 liters. I convert that to milliliters. That's more convenient for me to work in. For 7.29 milliliters. And that's a very typical sort of titration problem that you might need to do. And actually, we're not going to worry about that one. We're not going to worry about the mass of that. And I had the answer right there. Yeah, and we'll end here. So sometimes, and so I mentioned that we have to standardize. KHP is a primary standard that's used to standardize an NaOH solution. NaOH is one of those solutions that if I mass it out, I can't necessarily trust that the whole mass is just NaOH because water molecules stick to it. And so we have to standardize an NaOH solution against KHP. The two react in a one-to-one ratio. And so let's say that I make a solution of NaOH. I need to know what the actual amount or what the actual concentration of that solution is. So I standardize it against a KHP standard. I start with 0.285 grams of KHP. I dissolve that in water. I perform a titration, just like I showed earlier, and I use phenolphthalein. So when the titration is over, I've added just enough of the NaOH to react with all the acid that was in there. And so the way that you would perform this calculation, so we want to know our concentration. So in this case, we begin with 0.285 grams of KHP. My reaction is over. It turns pink when I've added 17.4 milliliters of NaOH. I want to know the concentration of NaOH. So remember our concentration. We want molarity, which is going to be our moles of NaOH per liter. We're going to find the moles of NaOH based on how much of the KHP we had to begin with, 0.285 grams of our KHP. Because remember, like I just said, the end point of our reaction is when I've added enough of the sodium hydroxide to equal the moles of KHP that I had to begin with. So I'm going to take my 0.285 grams of KHP, and I'm going to divide that by my molar mass, 204.222 grams of KHP per mole of KHP. And then I know that it's a one-to-one relationship, 1 mole of KHP to 1 mole of NaOH. And that tells me, so 0.285 divided by 204.222, that tells me that at that endpoint, I had 0.00140 moles of NaOH. So that 17.4 milliliters contained 0.00140 moles of the NaOH. So now I'm just going to take that 0.00140 moles of NaOH and divide that by my 17.4 milliliters. Converted to liters, so 17.4, I need to convert that to liters in order to, and I don't know why I'm putting this into my calculator, I should be able to do that. It's been a long week. 0.0174 liters. We're divided by 174. Remembering that those are the units of molarity, moles per liter. So I have a 0.0805 molar solution of NaOH. And so that's just using some basic stoichiometric principles and basic solution stoichiometry. And so that is all for today. And that is it for our discussion of stoichiometry. Next, we're going to be going on in our lectures next week. We're going to be starting to discuss the energy and the amount of energy involved in various changes of matter, both chemical equations or both chemical reactions, and actually looking at the energy involved in some physical changes as well, the energy required to do things like boil a sample of water, things like that. And so we'll have about 3 lectures associated with energy, but we are at this point now halfway through Unit 2. And so you should be starting to think about the Unit 2 exam. It will be here before you know it. And so be thinking about what you need to do in order to prep for that exam. Your Unit 2 exam is going to be harder than the Unit 1 exam. I guarantee it. These concepts are more difficult. There's more math involved. It is going to be a harder exam. And so start thinking about your preparation now. So that is all for today. As always, email me if you have any questions. Go to the LA session, see a tutor, do what you need to do. But in the meantime, I obviously need to go wash my hair. And so that is what I am going to do. And I hope everybody has a great day. Bye.